Hello, my friends. This is Dr. Mohamed Nezami. Again, with another video on RF and microwave device and system designs model. We have finished, you may recall, we have finished at least more than 35 videos on the design of various aspects of RF and microwave circuits using ANSYS HFSS for passive components. And then we moved on to from antennas to couplers to SIWs. And then we moved to a series on the SystemVue, Pathwave SystemVue simulation and design, and these are the videos right here. I urge you to please, if you could, go to the videos if you like, and subscribe. Please subscribe to my channel so we can get the number of members beefed up a little bit. That helps the videos. And if you feel like you can support this effort, please do. In the more information section, there are ways that you can support. I would appreciate that. Again, I'm an independent design consultant. I design RF and microwave circuits. I operate out of Jerash, Jordan. Very inexpensive compared to operating from the US or Europe. Most of my clients are from the United States and Europe, and some are from Asia. I'm looking forward to getting more clients, especially in the area of training on, as you know, let me just show you that. Let's go to that slide. I do have a series of trainings, one on HFSS. I hold that periodically at this nice hotel here in Jerash. If you have a group of employees, engineers, scientists, graduate students that you would like to attend, I can customize a package for you, very reasonably priced for 3 days for this much. And this even includes the hotel accommodations and some field trips and the meals, daily meals. I also have two sections of training on Pathwave systems, one for the system design, similar to the video I'm going to present today on 5G and 6G transceivers. And then I have another one, which is on Pathwave advanced design systems, which is more at the circuit level, at the component level. Okay. Please subscribe to my channel. This is the channel name here, Mohamed Nezami at RF_microwave. I believe we have about 499 subscribers. We need to get that at least to 1,000. I would appreciate if you could subscribe. Thank you very much. Today's video, we're going to start a new series on 5G transceivers. Okay, 5G, 6G. As you know, 6G is just a sort of like a back-end development iteration from 5G. The hardware of 5G is still the platform on which 6G is implemented. So I'm going to be focusing on what we call 5G, but it's really applicable to 6G as well. This is my phone number. You could contact me if you have any opportunity for design consulting, or you can email me on this email. So like I said, today we're going to start a new series on the 5G, 6G cell transceivers. Okay, so cell and customer premises equipment, CPEs, and user equipment also. We're gonna, same thing, it all applies together, except the, I'm more focused on higher power level ones for small cells, okay? So let's just talk about the system, the equipment side of where the RF transceivers on fifth generation personal communications stand out. We have this cartoon here that I took from the IEEE publications that shows various scenarios of the 5G, 6G networking. And you can see that we have classified the cell sites as these types, okay, where we have macro cell, which is, for instance, that encompasses a whole area of a radius, covering a radius of 30 kilometers, for instance. Now, this macro, as you can see, it covers a small town or a neighborhood of some sort, an area. Then it's divided also to accommodate the higher capacity to demand in specific areas such as schools, stadiums, high-rise apartment buildings. We have all of these types of cells that we have. We have macro cell, which is covers about 2 kilometers. And you can see here, you know, it could cover a stadium and a neighborhood, for instance. We have the femtocell, which covers 100 meters, okay? And femtocells, basically, they're like, as shown in here, for instance, you can have one in your house. In fact, I'm talking to you right now. I'm gonna be uploading this video using a similar setup where you have a router from a cellular provider that covers your house, and you could hook via Wi-Fi to it or Ethernet. And then we have, of course, the a whole different other classes. We have the picocell, okay, and the femtocell, which are similar. We have a relay cell, which is like this here, okay, where it's sporadically, sparsely out there somewhere far from the main covered area, the system operator area where we also cover. Now, the reason I'm interested to look at this, even though I'm going to be covering today a design of a transceiver, we're going to be covering as we will show you in a minute, there are two frequency allocations that are distinct for 5G. We have the sub-6 GHz or sub-7 GHz, some people call it. And then we have the millimeter, okay? We have equipment that operates from LTE all the way to 7 gig, which uses a specific technology. And then we have another area, which is the millimeter, which is out there from 24 gigahertz to 50 gigahertz, which needs another technology to deal with. So I'm going to have two sessions, one session where I demo the design of a transceiver for 5G in the sub-6 gigahertz, and the other one is in the millimeter one, okay? So, but if you look at the power level, okay, we can see that the power level of the base station or the cell side transmitter can vary anywhere from the macro cell is 46, as you know, 40 dBm is 10 watts, so 6 is doubling twice, so that means it's about 40 watts. And then we have some that are 1 watt, like the micro cell, and these ones here, the radio remote head and the relays are just a little bit above 2 watts, okay? And then the rest, which I will be dealing with here, is all in the milliwatt region. These are small coverage areas where you're only interested in covering hundreds of meters, okay, for high capacity. And of course, we have a concept which we will cover in a minute. Now, these sites utilizes multiple antennas to transmit these signals. So we have a MIMO and we have beamforming, okay? And the MIMO is used at the sub-6 gigahertz for capacity increasing. And then the beamforming is used at the millimeter waves specifically to do tracking and focusing the beams to a specific area that have more demands on data. So the interest right now in here is to show you this is because we have to size up the EIRP and from the transmitter power to size up the power amplifier size, okay? Now, like I said a minute ago, we have two distinct frequency allocations for 5G, and they're all designated with N and some numbers. These are for new, I guess, new N is for new, because they were really new to the LTE. So they designated them with numbers, but you can see that the sub-6 gigahertz, although it doesn't include here the 7 gig partition, it's somewhere between 3 gigahertz and 5 gigahertz, okay? Where the millimeter one, it starts out from 24 gigahertz all the way to, even though it's not listed in here, it goes up to like, let's see, the 40 gigahertz, okay, or 43 gigahertz. And these designations in here specify the bands. And the reason we're interested in knowing these allocations is because we have to use off-the-shelf electronic parts that are made specifically for that band, okay? So as you can see from here, the sub-6 gigahertz, as I will show in a minute, when you're designing these transceivers, with the advancement of data conversion or analog to digital and digital to analog conversion, we are able to actually go from bits to antennas with these. And that's what the transceivers that I'm going to demo, they don't use any kind of frequency translation. There is frequency translation in the digital domain, in the DSP domain, and the signals are just basically put out using DACs on the transmitter, and on the receiver that we go directly into the ADD without any frequency translations, because there is really no need to. We are able to utilize analog to digital converters and digital to analog converters that operates with gigasamples per seconds. So these are this enables us to actually direct sample the signals in these frequencies. So the transceiver is very simple, straightforward, because we don't have any frequency translations. We don't have synthesizers, local oscillators to use, nothing, okay? Where of course, these ones in here, millimeters, we really have to do frequency translations, because what we do is start out with first stage as an intermediate frequency. We can utilize this technique here where we can put out the signals somewhere below 6 gigahertz, okay? And then from there, we can have as an IF. So the IF is 6 gigahertz for these transceivers that are in this band here. And then we up convert and down convert in the receiver case to an IF2, and from the IF of 6 gigahertz up to these frequencies. So, okay, so we're going to show that in a little bit. So again, what we have two subclasses of hardware developments when we're dealing with building equipments for 5G, whether it's on the user equipment, the CPE, the customer premises equipment, such as routers, or at the tower base station. We have either a sub-6 gigahertz or a millimeter wave. And like I told you, the sub-6 gigahertz, the trend nowadays is to utilize direct bits to antennas. We don't have any frequency translations. We just play the signal, the modulated signal into a DAC, and then we filter it to get appropriate carrier. The move around within the from 6 gigahertz down to say 2 gigahertz, we move around in the digital domain. We frequency rotate the signal in the DSP, and then we just filter and amplify and directly drive the power amplifier to the antenna or the antenna panel in this case. However, in the millimeter wave, because we have to go up to operate in the 24 to 40 gigahertz, what we do is we have an intermediate frequency. So we bring down the frequencies from 24 to 40 gig down to a sub-6 6 gigahertz IF. And you can see that it's beautifully because you can recycle the sub-6 gigahertz IF section that you design here. And that's what I'm going to do. We're going to design first a sub-6 gigahertz transceiver using off-the-shelf components that you can buy, purchase from using Mauser and DigiKey and other distributors. And then, of course, in this one here uses different technology, a lot of MMIC usage at the millimeter microwave circuits. What we're going to do is we're going to use a frequency translation, a single conversion, okay, of translation from the from the IF, which is at the sub-6 gigahertz region, to the millimeter. Now, to do this, so let me put that here first. To do that, so we can see that we have two topologies on the radius, okay, and I drew the transceiver diagram from the receiver point of view, but all you need to do to see the reverse path, the transmit path, is reverse this amplifier in here. So we have two types. We can either, for the sub-6 gigahertz, we can receive it directly by digitizing from the antenna after appropriate amplification and filtering, or we could bring it with a single conversion to baseband and then digitize it. And the reason I did this, because we don't do this discretely. We actually have ASIC solutions, RF ASICs that will do this, that has a multi-channel analog to digital converters and multi-channels digital to analog converters that includes a front end that brings the signal down to baseband or near baseband and directly sample it. Where in this one in here, we're sampling a real IF. Okay, so we don't have a conversion to a quadrature conversion like we do here. Okay. Now, for the millimeter wave, because we have to really include a stage of up conversion, okay, or down conversion. So we, like for instance, in the receive case, we bring in the signal and amplify it and bring it down with this mixer with the local oscillator down to a sub-6 gigahertz, and then we go into the A to D. Now we could also utilize the direct conversion method, okay, where we can actually come in and directly come down to a baseband. You could, if you want, also in this topology in here where you have an IF, utilize this here as well. You can go in at an IF of sub-6 gigahertz and then again bring it to baseband like you do in here. But why should you? Because we have capabilities of ADD directly digitizing this IF in here, and then wherever that alias that belongs to the baseband or the passband happens to be located in the digital domain, we just rotate it mathematically to baseband. Okay, so that's the so what we're going to do is we're going to have the for sub-6 gigahertz transceivers directly from DACs and ADDs to FR1, the frequency allocation R1, which is a sub-6 gigahertz, and no frequency conversion on this type here. Where the other one, there is a single frequency conversion from 6 gigahertz to Ka band. I just chose 6 gigahertz because of commonality to this, so that when I design this section, I can recycle it for a transceiver that is operating in the millimeter. Meaning, really, you could literally take an equipment that was designed for sub-6 gigahertz and utilize the low power section of it, and then, or even the higher power if you need to bring it to a macro level, power levels, and then utilize it here, okay? Now, another thing I wanted to show that we really, there is two distinct, there is for duplexing, we have TDD, which is time division duplexing, and we have frequency division duplexing, FDD. And that's one of the differences also between sub-6 gigahertz 5G and the millimeter waves, is that the millimeter wave does not include frequency division duplexing. And in a minute, I'll show you the differences where this one does. So these here, you're always in the millimeter, you're always either transmitting or receiving. You're never really simultaneously transmitting and receiving at two different frequencies. However, for the sub-6 gigahertz, we do have some waveforms that are specified to be frequency duplex. And in that case, we don't utilize any, there is no common paths between the transmit and receive. Okay. Now, this here shows the differences, FR1 and FR2. Of course, this is the millimeter section, and this is the sub-6 gigahertz section of the frequency allocation for 5G. We want to point out the architecture that is specified by the standard for multi-antennas. So the antenna complexity for the sub-6 gigahertz and the millimeter, they're really the same. Okay, they come in as either 2 transmitters, 2 receivers, or they start out building all the way until you can get to 64 transmitters, 64 receivers. Okay, and in a minute when we start, we demo the designs of the array antenna for these, we will show you in a minute how that we're going to do that and how that impacts the coverage and the ERP and so forth. So for FR1, FR2, for the sub-6 gig or the millimeter, they both have the same antenna complexity they can have, okay? Of course, now this is specified. Now, when you go into macro level, it's really different numbers of antennas. The size of the array is different than the size of the array for example, the user equipment. The user equipment, as you know, the phone, they're most likely going to have 4 patches for an array of 4 elements only. Where for CPE, you might have 16 elements. And then for micro, you start getting into 32, 64, and 256. So 256 is about the highest I've seen being advertised. So in that case. Now, as far as MIMO, multi-input, multi-output, for the FR1, they're mostly using it to maximize capacity, because as you know, since you're using beams in here, you could utilize the same frequency. Different beams will carry different frequencies and therefore different transmitters at the same frequency, even though they're in the same system, but they have methods of how to actually utilize that, and that's what it's used for. Where for the FR2, it's limited. It's 2 by 2, 2 transmitters, 2 receivers at most, and it's mainly really it's beamforming. It's not spatial multiplexing. What I mentioned to you earlier, when you send the same different information on different beams, that's called spatial multiplexing, because you're really using the same frequency, but and you're using you're sending different information on different beams, even though they're at the same frequency, but they're spatially, meaning radially, they're really separated or orthogonal. Okay. Now, as far as the waveform modulations, they're all the same. Both bands carry the same thing. We can use anywhere from 64 QAM down to the BBSK. Now, when we talk about the transceiver design, we really have to size up the power level from the power amplifier. And the way to do that is that we really start out with the EIRP, okay, the effective isotropic radiated power. And that's defined simply as this. We take the transmitter power, and then we in dBm, and then we have the gain in dBs, the antenna gain in dBs, and we subtract any losses. And here it says cable loss, but it's not really cable. It might be just a trace that includes an isolator, for instance, that is a little loss. Whatever loss between the antenna and the power amplifier, you subtract that and you add these 3 things together and you end up with the EIRP, okay? And why we do this is because the system engineer will give us the EIRP, and you, as a hardware designer, will take that and interpret it into size the transmitter power amplifier size. Now, for receivers, for whether it's CPE or base or or user equipment, most likely the receiver sensitivity is going to be the same for all of these. Now let's start out with a simple example of showing you the principle of ERP. We have here a panel antenna that includes 1, 2, 3, 4, 5, 6, a column of 6 antennas, and they're dual polarized, and that's what the color stands for. They're 45 degrees offsetted in polarization. We have 12 here total and 12 here. Okay, so we have 6 plus 45 degrees might be, and 6 plus 45 here, so 12 plus 45 degrees and 12 negative 45 degrees. And the way to calculate the ERP out of this, if you know this is the hardware that we're trying to design here. We have 4 transmitters and 4 receivers, okay? And we want to design the transceivers in here. We want to design 4 sections of transceivers for this system. Assuming that mostly these dipoles, they're mostly 5 dB dipoles, okay, as a single element, okay? Now the antenna overall gain in this case, if you have every antenna in here is 5 dB, so the overall gain really is nothing but to multiply the signal by the n numbers of the elements. We have 12 elements, okay? So it's really 5 dB plus, and actually this calculation was based on the fact that they're all, okay, well, this is for either the plus 45 degrees or the negative 45 degrees, because we have 12 antennas of the same polarization, 12 reds, 12 blues. So the 5 dB plus 10 logarithmic of 12 is equal 15.8. That's the overall panel gain. Now the EIRP, as I mentioned earlier in here, so you take the total gain and then you add it to the transmitter, the Ph wattage in dBm, and then subtract 10 losses, and that should give you the EIRP. Okay, so in this case, we have 2 40-watt transmitters. It's just an example. We're using 40 watts, that's 46 dBm plus 3 dBs. That's like multiplying 40 times 2. So the ERP is equal to the total wattage, okay, from the PAs plus, okay, the total gain, and that gives you 64.8 dBm. An ERP for 60 dBms, that always represent a macro cell, because that's a very large amount of power that you can cover kilometers. Okay. Now, since these batches are always spaced at a half wavelength from each other, and the wavelength, for instance, for 900 megahertz is 33 centimeter, so you could actually estimate the size of this antenna. And in this case, it's we've got 2 lambda over 2s in here, and we've got 6 lambda over 2s. So that's most likely is going to be somewhere around 33 centimeter by 1 meter. That's the size of the batches, of course, but then you have to extend the dimension a little bit to accommodate the housing. Let's do another one at the millimeter waves. Okay, so we're taking an array in here that is made of this is, so got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's 16 by 8. Okay, so this one here has 128 dual polarized antennas. So it's really 256 elements. Okay. So we have 128, well, I call them vertical and horizontal, but in this case, they're offsetted really. So they're plus 45 degrees and minus 45 degrees, but nevertheless, same idea. So if the element gain again is assumed to be 5 dB for a single element, then the overall gain really for either one of the polarizations is 26 dBs, okay? And then assuming, of course, in this one here, we're assuming that the signal level, the wattage, this is unlike the other case, this is assumed to be for small cell or smaller size cells. So we're going to assuming it's 13 dBm, okay? And in that case, the total ARP, okay, is 13 dBm plus the logarithmic of the size of the thing in here, which gives you that the 34, okay? And then you add the 26, which is your overall antenna gain, okay? So the total power is 13 dBm, but we have 128 of them. And then you just add the overall, the panel gain, and that gets you to 60 dBm, okay? So you can see that, of course, this one here, unlike this case in here, this might have 4 transmitters, but this one has 128 of them for each one of the polarizations. And in a minute, why we're interested in this, because we have to design as an array of transceivers to serve this panel, okay? Now, again, since we've got 16 of them here, 16 half wavelengths, so that's 8 wavelength, and we have 8 in here half wavelengths, so that's 4 lambdas, and of course lambda is 1 centimeter at 28 gigahertz, so that gives you this whole panel is just about 8 centimeters by 4 centimeters. Okay, so you can see that this could very well be a small size, and that has to do with the small wavelength being at a high frequency. Now, on the receive side, as a hardware, as a hardware engineer, you sized up the PA size from the panel, or you size the panel from the power. Either case, you arrive at the power amplifier wattage level, because you want to design, you want to know how much you have the DAC. If you go directly from DAC to a PA, you have the DAC level full scale, and you have the PA. Now you sized up the wattage, and so you go pick up the devices from the catalogs, and you end up with knowing exactly how much overall gain you would need from DAC to PA output. Vice versa. Now let's do the same thing for receiver. Okay, in the receiver case, let's just assume that we have an ARP 50 dBm, and the signal can vary at the frequency that we're operating in, and this happens to be 28 gigahertz again. Is anywhere from minus 30 dBm to minus 40 dBm over the range of 50 meters to 300 meters. Okay, so when you're doing this now, we can see that the highest signal level that we can get is minus 30 dBm. So let's make as a requirement from a receiver that the input 1 dB compression point would be at minus 25 dBm with 5 dB margin from headroom from the maximum signal level. Now, the bandwidth specified for the millimeter regions, it's about 400 megahertz in most cases. And if you're utilizing the 64 quadrature amplitude modulations with an error vector magnitude less than, say, 8%, that here requires your signal to noise ratio to be more than 22 dB, okay? And typically the noise figure, as I will show you in a minute, when we demo design and model using Pathwave SystemVue, one of these transceivers, on the receive side, using off-the-shelf devices of these beamforming chips, if you don't use a front end to it, usually the noise figure and the losses add up to about 8 dB, 7 dB, 6 dB, that sort of a number, okay? So from that, we can see what the minimum signal that the receiver should detect, which is the thermal noise, okay, the KTB, minus 174 dBm per hertz. You add to that the noise figure, okay, because that's a noise gain. And then you add up the integrate over the bandwidth of 400 megahertz. So that gets you this number here, which is minus 58 dBm. And as we can see here, we said that the minimum signal that we receive with this much ARP, it's about minus 45. So we're going to specify the receiver to be at minus 58 dBm, which means it's got like 10 times more sensitive than the minimum signal that you can have in here. So this is appropriate. Okay, now to size up the receive path. So this is what you're picking up. Okay, so now given the fact that your ADD in most cases the full scale is 0 dBm, and to get this to the full scale, you would need your gain, of course, would have to be 58 dBs, which means that between you take the received signal minus 58 dBm to get it in an appropriate level to the ADD in the receiver, you have to get it at least to 0 dBm. That means you have to amplify this by 58 dBs. Okay, so that's the gain. And that's how we size the transceiver. Okay, just to give you an example of what's out there on the net when you search for these 5G, 6G transceivers. Here's one that I picked from this company, and there's no particular reason that I picked this company. I'm not trying to advertise, but there's several of them, many of them. All the major equipment manufacturers, they manufacture these equipments. Like this one here, for example, is for the 3300 to 3800 megahertz, which is a sub-6 gigahertz system. And you can see here that the transmit power is only 25 dBm, okay? And then the receiver sensitivity is minus 89 dBm for 3 megabit per second. That's much lower than what we have previously, but that's because it's only over a bandwidth of a few megahertz. Okay, that's not the sensitivity in here. We says it's minus 58. That's for the entire 400 megahertz, and that's why this is much lower. Okay, and of course it's always 2x2 MIMOs. That's the minimum that the standard dictates. Here's another example from another company. The name is here. So again, 2x2 MIMO, channel bandwidth is 100 megahertz in this case. And so they're specifying it with all the specifications in here, given same thing, okay? Now, for sub-6 gigahertz radios transceivers, the design that we're going to demo follows really this, and I took this out of the microwave journal, lots of literature on this aspect. So as you can see in here, this is a time division duplexing where we have an antenna that is shared by the transmit path and the receive path. And the way we switch back and forth between transmit and receive is by just basically when we transmit, we power up this section. The signal comes in out of the digital section, which is includes the DACs, digital analog converters, and analog to digital converters. There is no frequency translation, so there is no local oscillator, nothing. We just go directly PA after, and then we go and we have a circulator that duplexes the transmit and receive path from the antenna. And we have a filter in here, of course. Now, the low noise amplifier is switched here, and that's because of when we transmit, we switch over the path here to a 50 ohm termination so that we don't damage the LNA when high power reflections or signal doesn't have appropriate isolation from the transmit branch, okay? We have other things in here that we can see. We're sampling the signal with a directional coupler into a dedicated receiver, which is called observation receiver. And that's, as I will show you in the design that we're going to do, although we're not going to cover in details what the digital processing in here, that's used for calibration and linearization of the PA. So we can utilize this to do, for instance, power controlling, power level control, automatic controlling. We can monitor the spectrum. Like I said, we can pre-distort the signal so we can linearize the power amplifier. These power amplifiers are mostly going to be Dorothy, so they're very efficient, but they have a lot of distortions, and they can't really pass the compliance for emission compliance. So we have to take the signal output, take it in and compare it with the input signal and do pre-distortion algorithms in the digital domain to try to cancel out the inner modulations. Okay. Now, we have, of course, here the a little. In this case, we have a protection method of overpowering whatever, so that's not an issue. Now, let's look again, like I said in the beginning, the sub-6 gigahertz specifies both frequency division duplexing and time division duplexing, okay? Where the millimeter 5G allocations all specify only time division duplexing. So there's no reason to use any frequency duplexers. But this one here shows a diagram which shows you both the time division duplexing, and this is two antennas, two transmitters, and two receivers. So it shows you one path, which is one transmitter, and of course the receive path, and it shows you the other one in here. Okay, so this is most typically is the basic ingredient of a user equipment or customer CPE or the cell site, small cell, you would need. Okay, so the time duplexing is happening, is utilizing the a single antenna for both transmit and receive, utilizing a circulator, and the characteristics of a circulator that's one-way direction of propagation. So you can go only transmit to antenna where the receive signal come in and just goes the same direction goes to here, and nothing goes out back to that. Now, frequency duplexing, it's exactly the same thing, except we use a ceramic diplexer or duplexer in this case. Okay, so we basically have the antenna, we feed a 3-terminal device, which I will show you a lot of vendors make these mini circuits, CTS, a lot of Taiwanese companies and Chinese companies makes them as well. And so because we have the transmit is at a certain frequency and then the receive at a different frequency, so we have to separate them with this duplexer in here, okay? And it's just, other than that, it's exactly the same, okay? So there is. Now, let's start building the basic blocks of the sub-6 gigahertz and the millimeter gigahertz transceiver. And I only happened to I borrowed these from analog device application notes because I just didn't want to redraw them. They're very standard diagrams. Okay, so these are 3 different topologies of receivers that are used for the transceiver that I'm going to be presenting. So the first one is the direct one, where we go from the digital section, we go directly from the digital to analog converter. We go, I'm sorry, this is the receiver, where we go from the antenna all the way to the analog to digital converter. There is no frequency translation. All you have to do is just amplify the signal. You're getting a small signal like minus 60 dBm. You want to bring it up to at least 0 dBm at the 80D. So all you need to do is just get rid of the interference using these filters and amplify the signal level, and you're done. Okay, that's because this 80 analog digital converter is operating at gigasamples per second. And right now, the state of the art commercially ones, we have 6 gigasamples per second, and it can actually have a bandwidth that covers all the way to 7 gigahertz. So the front end. So you subsample it with that, and you do all your frequency allocation and rotation to baseband in the digital domain. Now for millimeter waves, because the ADC, it's beyond the range, the input range of the ADC. So what we do is we have a single frequency conversion, and that's what we're gonna do. So I'm gonna have 2 sessions. This session, hopefully, I might not get to it. Actually, 3 sessions. We're going to have this session, which is an introduction session, and then we're going to have 1 session of sub-6 gigahertz transceiver design and the millimeter design. Now, likewise, we could have a direct conversion, okay, and this can be utilized actually for both, either sub-6 6 or the millimeter. However, I really wouldn't want to recommend this here unless you're trying to use lower power ADDs, because in this case, you're most likely going to be sampling somewhere on the order of 2 or 3 times the bandwidth, and the bandwidth happens to be in a few hundred megahertz, not gigahertz, like in this case in here. So this would be a few hundred megahertz, and not like this, unless you're digitizing a signal that is like, say, a gigahertz bandwidth. Okay, so you have 3 different classes. Okay, and of course, all of these in the back, they're really the way to relay the channel the samples, the data back to the digital suction is using this just 204 digital interference, which is a gigabit per second switch that routes all this samples back to the digital the signal processing, where all the decoding, demodulation, and is done. Okay, and routing. Now, how do we implement these? We have 2 ways. Okay, we either use discrete ADDs and DACs from companies like Texas Instruments, TI, Analog Devices, other vendors as well, or we can use some of the ASICs, and there are some companies like Xilinx, for example, the system on chip series that basically includes ADDs and DACs that are running in the gigasamples per second. So, like, for instance, their latest is these up to, this one is up to 7. So this covers the entire sub-6 GHz. So all we need to do for a radio to implement a radio transceiver for sub-6 GHz is one of these Xilinx FPGAs, which has in it DACs that are running at 9.8 gigasamples per second, so 10 gigasamples per second, and there's a number of them. So you have either 6 of them at this speed, or you have other combinations as well. On the ADD, it's a little bit slower, so it's about 6 gigasamples per second. Okay, so all of these is one way to utilize to do. So all you need to do in this case is just have the PA section and the LNA section, and boom, directly you're right into the digital domain using these. Now, this shows a block diagram of how you would do this. For instance, the DACs out of the FPGAs, you could come out at minus 20 dBm typically for these waveforms, because the peak to average, you can come in out of them with 0 dBm for CW, but of course, when you modulate it over hundreds of megahertz bandwidth, you really need to back off the signal so that you can accommodate the peak to average ratio. So you operate down in the minus 20 dBm out of the DACs and the FPGAs. And so to get to, say, 40 dBm, okay, 10 watts, all you need to do is have about 60 dB of gain chain to get to it, okay? And the receive section, same thing as well here, so very straightforward. If you're using quadrature technique, you could utilize, the only thing you would do here is double up on the DACs and the ADDs, okay? And you still can utilize this same exact chain, okay? Now, if you don't use FPGAs, you can use discrete ICs, okay? And discrete ICs, we have Texas Instruments, like I said, we have analog devices. Also, we have Curve, we have mini circuits, we have others as well. And we have a whole bunch of startups that have chipsets for 5G, especially for beamforming, as I will show you in a minute. So you can utilize one of these chips. Like, for instance, this one here has 4 transmitters and 4 receivers in it, digital ones. Okay, so these are DACs, and they don't have any RF parts. These are just digital to analog converters and analog to digital converters. Okay, so all you need to do again is just basically include your PA and LNA, and you're done. Very similar to the case of the FPGA. These can run faster. They might be cheaper from an FPGA, but they are really competing nowadays with Xilinx on this market. Okay, so this is a demo of how you would design a 4x4 4 transmit, 4 receive, including a feedback path for, as you can see here, these are the observation receivers. Okay, what these do, they observe the PA, okay, and signal feedback that PA signal and enable you to do some digital signal processing. Also, by the way, there are ways to play a signal into the receiver front end, and we have those, okay, to calibrate the receive path as well. Okay, so we have that as well. We'll show you in a minute. Some of them have it. Now, here's another chip that has the basically, this is the 89988 in this year of 2023, because if this video stays for long time, they're going to be looking at this saying, oh, how primitive it was back then. But this is really the state of the art. So the DAC in here, these are 4 DACs, 4 receivers, and they include all the digital signal processing behind that to process the waveform. Okay, and so this is 12 gigasamples per second again. Okay, so this enables you to really play signals and digitize signals up to 7.5 gigahertz, which is really good. You can go to the website of analog.com and look at this chip, tons of data on it. Same thing in here. This is from TI, okay, just to be fair for these companies, then they've done marvelous jobs at these comments. So this is a 4 transmit, 4 receive ones as well, okay? So you have 80D, there's 3 of them in here, and there's 3 of them here. One of those is used for observation. They called it in here, they called it FB, which means feedback, okay? This is dedicated for observation, okay? And of course, the DACs, we have 2 in here and 2 in here, and these are used to play the transmit signal. Now, also, as you can see here, we have chipsets that include actually the front-end quadrature up conversion and down conversion. That's where you like this is an example 89371. Okay, that's where it includes the analog digital converters with a quadrature front end and the DACs with the front end. And they also have ways to monitor. They have observation receivers for either the to route to feedback the PA signal, or to observe other signals as well to perform interference mitigations and so forth. They have also, they include in these chips is the digital signal processing section, and that is shown in here basically. This is in the old days, that's where you would, of course, the 80D and DAC all the way to the just 204. So meaning this is the digital signal processing chain is completely done in here, okay? So I'm going to end it at this before I start my next session, okay? And again, I just want to remind you, if you're interested in the training, I have these 2 trainings that are done. So you can reach me if you're interested at this number, at this email. I also, like I said to you right now, I'm running a special. If you need to outsource a design, let me know. It's $20 an hour. We're working for boards, and I turn in the Gerber files and the schematics and design files and work with you, even come in and help you, support you with testing if you like. So we're going to go on to the next part. So I will stop it right here and enjoy your day. Thank you for watching this. Thank you very much.